Okay, so just a quick little review of what we've been up to lately and where we're going to today. So over the last while, there's basically been one formula that rules them all in probability, and that formula is the number of possible outcomes over the number of favorable outcomes for a particular event that you're trying to find the probability. So that is the main probability equation, but we basically over this unit have learned how to do Venn diagrams. We've learned how to do tree diagrams, and these help us understand the possible outcomes and the favorable outcomes. And then today, we're going to look at something called a two-way contingency table. So these have been the three main tools that we've looked at. And then in addition to that, we've also learned about some identities. We've learned about the addition rule, okay, for any two events, and how if we have mutually exclusive events, all that means is there's no A and B, and so it simplifies to this. And we also learned about something called the complementary rule. And then today, we're going to have a little bit more focus on another rule, and this rule is called the independent events rule. And so if we know two events are independent, then if we know each of their probabilities, we can multiply them to get the probability of both of them occurring. Or if we want to check if events are independent, we check to see if this equality holds. Okay, so this is sort of a summary of the whole topic, and we're going to mostly live in this area over here and this area over here. Give me a thumbs up if this content looks vaguely familiar to you. Give me a thumbs down if this looks completely unfamiliar to you. Just want to get a feel for the people in the room. Okay. Hi, Lisakaya. So for those who are feeling unsure, remember, we've done 5 lessons before today, and they have focused around the Venn diagram, the tree diagram, and then this stuff over here. Today, we're going to focus on the two-way contingency table and the independent events rules. Okay. So if you are unsure of those things, go back and watch the previous recordings and life will be good to you, I promise. Okay, so let's get going on the actual lesson for today. So like I said, the main rule that comes into focus is if events are independent, we can use this equality to help us work things out, but we mainly use that in tree diagrams. But if we want to check whether events are independent, then we see that this equality will hold. And I'll give you an example of this from a two-way table later on. But let's just start with a simple two-way table. So what is a two-way table? Well, we have a two-way table has mutually exclusive events. So on the horizontal, the mutually exclusive event is basically gender, and the two choices are being a boy or being a girl. If you're in one category, you can't also be in the other. Okay, and then the other mutually exclusive events are on the vertical, and the choice here is between football, athletics, and other. It's your favorite sport. And so you can either have football as your favorite sport or athletics or have something else. So a two-way table has mutually exclusive events on the vertical and the horizontal. Now, first of all, we need to make sure that we can read off these information from the table. So if we look at this table for a year 7 class, how many boys chose athletics as their favorite sport? Can you tell me by putting it in the chat, how many boys chose athletics as their favorite sport? So you go and find boys on the horizontal, athletics on the vertical, and you should get the answer 4. Love it. Now, I want to know, looking at the table, what was the most popular sport with boys? Okay, well, the most popular sport with boys, if we look at the boys row, it's definitely going to be football because 10 of the boys chose football, and only 4 chose athletics and 1 chose other. Okay, fantastic. You guys are smashing this. Okay, next question. How many girls are there in the class? How many girls are there in the class? Well, we might need to do some extra maths here. I think what we need to do is we need to take this table and give it some rows for totals. Let's have a look. So girls, 5, 4, 7. So that should be 16. Yeah, so how many girls? There are 16. How many pupils are there in this class? How many pupils are there in this class? So we know there's 16 girls. How many boys are there? It looks to me like there are 15 boys, which means that the total number of students in the class is 31, because there's 15 boys and 16 girls. Now notice how helpful it was to have a total column, right? Like a total column for the horizontal totals. Okay, here's a bonus question from me. How many students chose football as their favorite sport? How many students chose football as their favorite sport? Now I see Annie and Lisa and Kanya and Tsirivatso have said 15, and I agree it's going to be 15 because we just look for the column like this. And using the same idea, there are 8 students who chose athletics, and there are 8 students who chose other. And what I want to point out to you is if you add up 15 plus 8 plus 8, you'll still get 31. Okay, now I'm going to bring in some probability. If you chose a random person from this class, what is the probability that their favorite sport was football? So if I chose a random person from this class, what is the chance that this random person's favorite sport is football? Well, we know 15 students out of something like football, and we know the grand total is 31. Okay. Okay. If I said to you, if you chose a random person from the class and you asked them, in fact, let's go with, what is the probability that a randomly chosen person is a let's say a boy? What is the probability that a randomly chosen person is a boy in this class? So that was a bit more tricky, but actually we just look and see how many boys are there. There are 15. And how many students are there in total that we're picking from? It's going to be 15 out of 31. Okay. Now, if I said to you, one more, then I'm going to move on from this example. What is the probability, if I chose a random person from the class, that they were both a boy and their favorite sport was football? What is the probability that a randomly chosen person from the table is both a boy and their favorite sport is football? So we know the total's not changing. It's going to be 31. But what is the important bit in the table? Well, you have to be both in the collection of boys and the collection of people whose favorite sport is football, which would be 10. And so the probability would be 10 out of 31, because you have to be part of both events. Give me a thumbs up if you followed that first table. Give me a thumbs down if you didn't feel comfortable with that interpretation, because that was what we call reading off information from a two-way table. Okay, awesome. Well, that's a great start then. So then let's move to another table. Now, in this table, it's a little bit more exciting. So what I want to do is I want us to look at this table, and it says that the hair color of 50 learners was recorded. And the good news is down here, I see a 50. I want you to work out for number 1, if you choose a random learner from this table, what is the probability they will have brown hair? So what is the probability that a randomly chosen person So I look for brown, and I see the total, and it's going to be 17 out of 50. Okay, what about the probability that I have blonde hair? What's that going to be? Well, I see the answers flying in there from Brooklyn and Neo. So you're right, 11 out of 50. What is the probability they will have black hair or brown hair? So black hair or brown hair. Now remember, or either of them is a favorable outcome. So what is, now my total's not going to change, but the or, well, black hair, there are 22. There are 17 with brown. So it's going to be 39 out of 50. So it's very, very likely you'll get either someone with black or brown hair. Okay, what's the probability somebody will have blonde hair or brown hair or black hair? Well, it's going to be 50 out of 50. And so that is going to be, there's 100% chance of that. Yeah, okay, so that actually wasn't so hard. I think lots of you could read that off. So what I'm going to do is I'm going to change the questions a little bit. So if I said to you, what is the probability of choosing a girl from this collection of students? I want you to work that out. So we'll call that question 5. And then for question 6, I want to be, what is the probability of choosing someone with, let's say, black hair? So what is the probability of choosing someone with black hair if you randomly choose someone from the collection? See if you can do those two. So the good news is we know this is out of 50, and we know this is out of 50. What's the probability that someone is a girl if they're chosen at random from this collection? Well, I go to the girl column and I get 24 out of 50. And then what is the probability somebody has black hair? Well, it's going to be 22 out of 50. Yes. Okay. So far looking awesome. What if I said to you, what is the probability of a randomly, what is the probability of a randomly chosen person being a girl and having black hair? So what is the probability of a randomly chosen person being a girl and having black hair? So girl, black hair. So there's the magic number there. And that is going to be 10 out of 50. Okay. Well, give me a thumbs up if you followed what I've done so far. Give me a thumbs down if you haven't followed. Just want to get a feel. The answers were flying in the chat, so I didn't see too many questions or comments that indicated any issues, but I would like to leave that open for all students. But things are looking good so far. Okay, well, let's keep swimming. So you guys have done so well. I think it's time for a sort of exam type question. So over here, I want you to try and do for me, I want you to work out first, what is the probability of a randomly chosen person? So that there are 80 learners in grade 11, and they were asked whether they played sport for their school, and the results were recorded in the following contingency table. I want you guys to try, I want you to try and answer A, B, C, D. Leave E out. I don't want you to do E yet, but I want you to try and do A, B, C, D all by yourself, and then we'll talk about what that means. And you can just put in the chat A or B, etc., as you feel comfortable. Okay, so I see some answers coming in for A. So I'm pretty confident it's going to be out of 80. And female, if I look at the female row, there's a 50 out of 80 chance that a randomly chosen person will be female. So the sample definitely has more females in it than males. Unless I'm adding up wrong, but 21 plus 29, yep, that gives me 50, yeah. Now, what about B? What's the probability that someone chosen at random plays sport? Well, I've got 80 students and 48 of them play sport. Yeah. Okay. Now, what about C and D? Female and play sport. Female and play sport. Which one would that be? So I go for female and I play sport. So there's a 21 out of 80 chance So there's a 21 out of 80 people chance that you'll choose a female who plays sport, or a female and they play sport for the school. Now, what about D? What about D? So female times play sport. Well, I worked up the top. I had 50 over 80 for probability of being female. Playing sports was that, and now I'm going to have to get my calculator out, and it might be easier to go into decimals here. So 50 over 80 times 48 over 80, and I'm going to write it as 0.375. Now, what I'm also going to do is I'm going to translate what C is into a decimal. So 21 divided by 80 equals 0.2625. Okay, so these are there any, before I move on to talking about E, are there any questions from students? You can pop your hand up if you want to clarify something. It's really important that you understand these 4 calculations so far and how I got them. Are there any questions? I'm just monitoring for any hands that may go up. Otherwise, I'm going to start talking about E. All right. Question E is about independence. It's the independence. Do you think sports preferences are independent of gender? Why or why not? So what they're asking us to say here is, if we know someone's gender, does it affect whether or not the likelihood of them playing sport for the school? And the way we would check this, the independence test that I said earlier on would be like, is the probability of A and B the same as the probability of A times the probability of B? Now that's the rule, but in our particular example, instead of having A and B, what we're going to do is we're going to say, what's the probability on this side? What's the probability of being female? What's the probability of playing sport? And then what is the probability of being female and playing sport? And so what you see is we're not using A and B, we're just using F and S. But I want to ask students of the room, do you understand how we need to check the red box? We need to check whether or not F and S, or the probability of F and S of being female and playing a sport, is the same as the probability of being female times the probability of playing a sport. Okay, I will repeat. So it doesn't okay, here's where it gets a bit more exciting. It doesn't have to be female. So if the reason I'm choosing this is we've already done the work for it, but if you wanted to check, you could also say, what is the probability of being male? Okay, you could have also checked this, the probability of being male and playing sport, but then you would need the probability of male times the probability of sport. And so that would also be fine because it's A and B, and then the probability of A and B individually. So it's only, you could have chosen either, but the fact is that I've already done the work for the female part, and so I'm staying with that. So let's just check this. We know that the probability of being female times the probability of playing sport was the answer for D, which was 0.375. So we know that, we worked it out earlier on. What is the probability of being female and playing a sport? It's 0.2625. Are these two values equal? Are these two values equal? They're not. Therefore, we say that sports preference and gender are not independent of each other. So what we did was, and I'm going to do another one of these, so don't worry. Like, if this is the first time you've seen this, it is confusing. And I didn't have to use female in sport. It's just that we'd done the workout already. So I thought, let me stay with that. But I could have used males in sport as well if I wanted. So the main thing I want to show you is that the two sides of the equation were not equal, and therefore sports preference and gender are not independent. Okay, should I show you? Let's squeeze in another one before the break, just so that you can see this isn't so bad. Give me like a sort of thumbs up if you followed that, or if you have a question, put your hand up and maybe I can assist you. You can ask your question. But I think another example will help. Okay, cool. Okay. Let me find one that is a bit more like this example. Okay, let's do this one. Okay. If I say to you, what is the probability that a member selected at random is female from this table? This is a survey. A tournament organizer does it with 150 members at a local sports club to find out whether they play tennis or not. we divided up into males and females in the survey, and those who play tennis and those who don't play tennis. What is the probability that a randomly chosen person is female? Well, we probably need a bit of extra stuff here, don't we? So I'm going to fill in these extras here. That's 80, and then that is 70, I guess. And then this would be 150. So the probability of being female when randomly selected is 70 out of 150. Okay. What is the probability of the randomly selected person being female and playing tennis? So I'm looking for female and playing tennis. So this would be, there's a 20 out of 150 chance of choosing someone randomly who is female and plays tennis. Okay, now that bit, I think you guys have got waxed. Now, this next bit, it says, is playing tennis independent of gender? Motivate your answer with the necessary calculations. I don't think we have enough stuff yet. We know the probability of being female from the sample is that. We know the probability of being female and playing tennis. So I'll just say playing tennis was 20 out of 150. What would we really like to figure out still to help us to check this? What is the thing that I need to work out over here to help me check whether these are independent of each other? What do you think I'm going to put inside this bracket? What do you think is going to go in here? It's going to be T, yes. So this is going to be the probability of playing tennis. So what do we think? If there are 150 people here, what is the probability that someone plays tennis in the sample? So tennis, I look for that column, and it looks to me like it's 70 out of 150. Awesome, awesome, awesome. Now we need to check what is this times this, and we do that. We also need to, we already know the answer to, well, we kind of do. We'll put it in decimals. So if we go this times this, what do we get as a decimal? So, okay, 0.22. And now, what is the probability of being female and playing tennis? It would be 20 divided by 150. Let's see what that is. That is 0.133333. So is gender and is playing tennis independent of gender? What do you think? Yes or no? So it's not independent. I actually left that out last time. Independent, as this does not equal. So P of F times P of T does not equal that. Yeah. Okay, so if we look at what we've done in the first half of today's lesson, we've learned how to read information in a two-way table, and we've also learned how to check whether or not the mutually exclusive events on the horizontal are independent of the two mutually exclusive events on the vertical. Okay. So give me a thumbs up if you're feeling a bit more confident now. Give me a thumbs down if you're feeling still a bit lost. Okay. Awesome. Well, then let us have a brain break, because we know we must take care of our brains, and then our brains will take care of us. So let's stand up for a moment, stand up nice and tall, and just roll those shoulders back and just loosen yourself up a little bit. So roll them back and then roll them forward. Okay. And then let's just do a little bit of turning, some light turning to start with, or rotating rather, I suppose. And as we get looser, we can just turn around. And then hopefully eventually you get close to 180 degrees. Or maybe some of you can even go further. Okay, let's loosen up our necks. So let's just take our necks to one side. And do the other side. Okay. Lean them back a little bit and then lean them forward. Yeah, shake out your arms. Shake out this arm. Shake out your legs. And let's do a stretch like this. What's this called? Tricep stretch. And let's do another one like this. Okay. All right, and let's get some cardio in. Let's go with air skipping, because jumping jacks just seems a bit too exciting for today. Okay, 3, 2, 1, let's go. 5 more. And then we go. Okay, and then let's see if you can do a quick Maths 24 puzzle. Oh, what's going on here? It's like double trouble here. So just see if you can do one of these two. Can you get to 24 using one of these two? Who can get to 24? Pop your answer in the chat if you want the glory. So I see Chegavatso, I see Annie, I see Sadiq, Samisiwe, and lots of students have, oh, there's a couple of ways of doing this. So 6 plus 6 times 2 times 6 plus 6 times 2 plus 1. And then another one I saw was 6 times 2 plus 1, which is 6 times 3 plus 6. And so that definitely gives us 24. Yep, I like it. I like it. Very nice. Okay, cool. Well, then you've solved that. Well done to everyone. I like the enthusiasm for Math 24. Let us return to our journey with probability. So I would like you, so now we're straight into old exam land, and I'm going to let you fly solo. So step 1, I'll let you do the whole question, but I will check in with you as you go. And the first step is you need to find the missing values A, B, C, and D. And you can either put your hand up and let me know audibly, or pop them in the chat. Let's see if we can do those first. How do we work out those missing numbers? over to you guys. You can do it. Keep those answers coming. Keep them coming. Okay, we've got A and B, but now how do we get C? I suppose if I wrote this in, it would be a little bit easier. Hey? What is D gonna be? Okay, so if you have any questions about how we got A, B, C, or D, you can put it in the chat, or you can raise your hand to have a conversation with me. But yeah, it looks to me like A, B, C, and D are we've done them. And so now it's a question of 10.2. How do we do 10.2? Okay, watch out for 10.3. The wording is a little bit different. So it says, given that a male shopper is questioned, what is the probability that he has broken his arm? So think about how many people are we actually considering if we know that we're speaking to all the male shoppers? I think we need to look at the male row and see that it's out of 350. So if it's out of 350, because remember, it says here, we're given that a male shopper is questioned, that is a condition that they've laid down. We're only talking to males. And how many males are there out of the whole total that's out of 350? So now we need to know, what is the numerator? What is the probability that he has broken his arm? Well, they're 210, it looks like to me. So if I look here, if you're a male, there's 350, 210 broke, 140 didn't, has broken his arm. So that should be 210 out of 350. Okay, now the last part of the question. Now you may have to go and find some calculations to help you with this, but it says, determine using appropriate calculations whether breaking an arm and being male are independent events. Now, what I like to do is I like to say to myself, you know, I write down what is the probability. They said to me being male, and also what is the probability of breaking an arm. So I first want you to help me work those out. So what's the probability of being male in this table? Now I have to think, what are we considering? We're considering the whole population, which is 575. What's the probability that a randomly chosen person is male? It's just going to be 350 out of 575. Okay, what about the probability? What is if you choose a random person, what's the probability they've broken their arm before? I said you're breaking arm, but broken arm or broke arm. What do we think that's going to be? Well, it's still going to be 575. Now I need to go and look here for broke arm, and that is going to be 290. Okay, now I need to work out a third one. What do you think is going to be inside this third bracket? So I've done two parts, but there's a third part that I need to check. What do you think I'm going to check? What am I going to write in this bracket here? So it's going to be male and having had a broken arm. Yes. Awesome. So what is going to be the probability for that? Lovely, Brooklyn, Morgan. Well done. Malcolm, Samisiwe. Awesome, awesome, awesome. So we're happy it's still 575, but now we need our table again. So let me zoom in. And I need to go and find male and broken arm people. So male and broken arm people, to me, look like they live over here. And so this is going to be that. Okay, so now I'm going to get Keisha. Can we unmute Keisha? I see Keisha has a question.
Hi, sir.
Hey, how's it going?
It's going great. So I have a question on P breaking arm. How did he get to 90?
How did I get to 290, you mean? Or
yes.
Okay, if you look at the number of males who broke their arm in the sample, it's 210, and the number of females is 80. So all I did was I added 210 and 80 to get 290. Does that make sense? Like I totaled them up. Okay. Just take a moment to think about that, but I think that makes it clearer. So for the decimals, let's get, so 350 divided by 575 times by, what would be the other one? Broke arm would be 290 times 290 over 575. And that would give us, as a decimal, it would be, if I round off to two decimal places, 0.31. And then I want to know what is the probability of M and, or I suppose I should just put the unhappy face, which is the official symbol, broken arm, and that is 210 divided by 575, and I get 0.37, and so therefore they are not independent. Yeah. Okay. So at the moment, most of our examples have turned out not, it is possible to be independent, but so far the data hasn't shown us that. So yeah, give me a thumbs up if you're feeling okay, thumbs down if you're feeling unsure. Maybe we can squeeze in one more question before we call it a day for today. Okay. Oh, let's finish with this one. This is another variation of these questions. It's a little bit different. Okay. It says here, given P of A is 0.2, given P of B is 0.5, and given P A or B is 0.6, where A and B are two different events, how do I calculate this? Now, in this case, we still can check in the next question, it's asking about independence, but we need to be able to work out what the probability of A and B is. So what do we need to do? What identity can I remember from earlier in probability? I think that there is a statement. See if you remember this one. So you don't just add them though. Okay. Give me a thumbs up if you remember this identity. Give me a thumbs up if you remember that identity. So you're right. This would be 0.2. P of B would be 0.5. And then P of A or B would be 0.6. So now I want to ask you, ladies and gentlemen, what does this bit over here have to be in order to make the world balance? Yes, Sadiq, exactly. It's the addition rule. You're right, this is 0.7, that's 0.6, but what does this have to be? Be careful. So this together is 0.7, but I want it to be 0.6. Yes, so this is going to be 0.1. And so we know that P, A, and B is actually, and notice it's and 0.1. Okay, so we use the additive identity here. Now, I want you to check, are the events A and B independent? And I want you to do that by yourself. Are the events A and B independent? What should I be checking? Malcolm, yes, let's unmute Malcolm. Yes, Annie, 0.1, yeah. Hi, Malcolm, can you hear me? Yeah.
Yes, sir. Good day. How are you?
Very good, very good. How can I help?
So I wanted to ask, there where we say P, A, and B, why is it 0.1? How did we get to that?
Okay, so the thing that is important is there's something called the additive identity, which says that for all two events that are different events, this statement is going to be true, where P of A plus P of B minus the P of A and B. Now, they told me A or B is 0.6, right? So I just simply plug that in. I then know P of A is 0.2 and P of B is 0.5. That's given to me. Now, together, we have a problem. Those two add up to 0.7, and that's bigger than 0.6. So what do we need to do Well, we need to make it smaller, but by how much? Well, we need to make it smaller by 0.1. And that's why we know that the P of A and B is 0.1. Okay. So I'm using this identity. I've got 3 of them, and I use the 3 to figure out what the 4th is. Now, in order to check if they're independent, I'm going to go P of A times P of B, which is going to be 0.2 times 0.5. So let's do what I get for that. And that gives me 0.1 or 1 in 10. And then I ask myself, what is the probability of A and B? And that is 0.1 or 1 over 10. So are A and B independent? Yes. A and B are independent because P of A times P of B is P of A and B. And that is a fantastic place to leave it on, or to finish off for this week.